This is Clarence and Kyle's project for Ivy Tech EECT 122 digital applications. We set out to see how we could control a motor with circuits that we learned about in class, particularly DC circuits. Since we already had a small DC motor, we continued in that direction. With a little research, it looked like we could use a 555 timer and use that as a pulse trigger to drive our DC motor. But we would need to use something that could supply a little more current. So we implemented an H bridge. Since the 555 timer can only output around 200 milliamps, our motor can almost draw a half amp or 500 milliamps. The H bridge can handle almost 700 milliamps peak per channel. Um, we modeled a few of the circuits in Multisim and finally decided on a double diode potentiometer setup, which you can see right here. Essentially, the potentiometer is in place of both the RA and RB resistors, and one diode jumps around one way and one diode jumps around the other resistor the other way. So we can use this pot and go off the center tap of it and vary the uptime and downtime of our pulse width at the same time. So here you can see we're feeding that in over here to our 555, and then the capacitors here to set the timing with, and then for our RC time constant, and then our black wire here is the output from the 555 to our little integrated H bridge. Just for looks, visual representation, we've attached an LED and a resistor here so you can see the average voltage as we change the pulse value. And hopefully the camera is not going to be too bad here, but I'm going to try to run this so you can see the LED. The motor we have a little bit of an issue with because at low speeds it doesn't always want to take off, so I might have to nudge it. So here we go. I'm going to show you how to start this up. Okay, and I'm going through the camera here, trying to figure this out. So I don't know if you can hear it, but it's kind of cool if the frequency as we go through it. Here I just kind of gave it a little nudge of a higher pulse, and we're going to try to run it here at a lower speed. You see the light actually looks kind of bright, but it's not full. It's easier to tell without the camera. So here we're running our motor. I don't know the RPM, but we're running it at about 2 kilohertz of pulse width to it, and at around 5 volts. Okay, so I'm going to adjust this, and I'm going to let you listen to it. We're going to raise the speed here. And take a look at the LED. It's pretty much on full. And then now our motor is getting full voltage, and we'll just bring this back down slowly. I'll let it run like right here for a second so you can see that it can maintain the speed. Okay, and we'll bring it down a little bit more. So the pulse width is actually driving the motor, but it's not resistance through the rheostat that's keeping it from making it maintain a speed. Where actually the voltage is being averaged through the windings in the motor from the pulses. So the voltage level on the scope, and I'll show you that in a minute, you can see it change, you can see the width change. So the average voltage that we're giving to the motor is actually the variable here. So I'm going to bring it back down to the other way. We're going to go low. So let me show you what this looks like on the scope. So see, the lights dim, frequency went up, but then it basically goes to nothing. So here I'm going to try to maneuver this and do this at the same time. So here's the signal on the oscilloscope, and it's saying that we've got a period here, or frequency, 13.5 kilohertz. And if you notice, this is 0 volts right here, and this is the on time portion, okay? And it's just barely registering on the oscilloscope. So I'm gonna try to run this up and hold the camera all at the same time here, and let you see how the duty cycle changes in the frequency. So we're barely coming on. Our frequency is around 4, 3, 2. So I got to nudge the motor to get it to move a little bit. And I'm going to bring it up a little bit more. There we are, it's spinning on its own. Low speed, 2 kilohertz, 50% duty cycle now, okay? And then we're just going to run this all the way up slowly. Watch the frequency, it pretty much stays pretty steady until we start shortening the capacitor time. So our frequency goes up. I'm going to adjust the trigger here down to where we get a better signal. And then here we go, we're almost full on. Okay. See that now? Now it's kind of looking exact opposite. This is top voltage, high voltage, and low here. Kind of some interesting properties happening here. So we'll go back down the other way, low. Oh, I would put, see how high we are. We're running about 18 kilohertz. So it's pretty high. So back down it is, kind of slowly. You see it go the opposite direction. And it's moving out of our trigger area again. And the other way, all the way pretty much off. And here's the circuit again. Thanks for watching.